Hello, everybody. This is Eyal. This is the first meetup in a long time that we have on location at Avality, which used to be the location of the Jacksonville Java user group and a lot of other user groups in Jacksonville. We are grateful to Avality to let us back into the nice facility. And of course, we are going to continue to have this in a hybrid format and have the meetups virtual at the same time. This enables us also to have great speakers from afar, like Adam that we have today. This is actually a joint meetup of the Jacksonville Java user group and the Enterprise AI and the newly formed Google developer group of Jacksonville. So we are going to run this meeting and it's going to get recorded. You can, people online can ask questions using the questions and answers tab or just through the messaging. And Adam will start this presentation in a minute. I just wanted to say that I'm very excited to have Adam. Combining AI, machine learning, and Java is something that I was always passionate about. It is sort of difficult it seems like it's difficult for Java developers to get into machine learning and AI because it seems that everything is done in Python. Yet you have a lot of Java developers, a lot of Java shops, and it's necessary, it's actually needed to be able to do that. And what Adam has done is providing a solution for a lot of these issues. So I'm very happy to have him here, and I'd like to get the word out about it. So I'm going to try to conceal myself and leave the stage to you.
Okay, thanks Eyal for the introduction. So I'm going to try and share things now, and please let me know if something goes drastically wrong with that. Okay, so as Eyal said, we're going to talk about Java and machine learning today. We're going to talk specifically about a library that my group at Oracle Labs has been making and is open source called Tribuo. We released it a few years ago. A little about me. So I'm a researcher in Oracle Labs Machine Learning Research Group. I've been in Oracle Labs for about 10 years, and I joined immediately after finishing my PhD in machine learning. So we're going to start off. I'm going to assume that most people know what Java is, or you'll know enough to get by. But you may not know what machine learning is. So we're going to start off with a sort of fairly broad introduction, which will be enough for the concepts we're going to talk about in this talk. So we're going to imagine we have some unknown function that takes in a float array A and then emits a float array B, and it does something in the middle of it. Now, if what we want to do is something called a supervised machine learning algorithm, we're going to take in many, many example pairs of A and B, and then we create an approximation to our unknown function, which when we give it A produces B. Now, this can be an if statement, like very simple as just an if statement with a threshold, or as complicated as 100 gigabytes of floats, and we have a huge number of matrix multipliers and lots of complicated things happen. Both of these are machine learning if we're going to set those parameters, that threshold in the if statement, or that 100 gigabytes of floats, automatically based on some of the input data. So if we want to think about a couple of example pairs of problems, we could have an array of pixel values, and then the probability of those pixel values containing a specific numerical digit. We'll see an example of that later. We could think for a more business problem, we could have the previous n quarters of sales figures, and we want to predict whatever the next quarter's sales figures is. Or we could have an array of integers that represent words in a sentence, and then we have a +1 or a -1 that is a positive sentiment or a negative sentiment for that sentence. So these are all tasks that we can use and apply machine learning to try and learn an approximation to the real function that provides those outputs. Finding that approximation is called training a model, and then the approximation is the thing we'll refer to as the machine learning model. Now, these sort of learned function approximations are quite different from other kinds of software. When we build a piece of software, we normally have the source code and we can inspect it and we understand how it behaves. Whereas at runtime for a machine learning system, we have that trained model, but we know nothing about how it was created or any of the information used to train it. And that model behavior depends very, very strongly on that data that was used to train it that's not present at runtime. How well it behaves for your particular task is basically a function of how close is the data to whatever you've actually specified the system to be. And if that data really does represent the task you want to try and solve, like an easy example for this is if you want to do face recognition, you need to have multiple genders and ethnicities. If you train a system entirely on white men, it will only recognize white male faces, and that's kind of a problem. So in addition to this sort of data-dependent behavior, the training algorithm that produces the model, which is also not present at runtime, has lots of different hyperparameters which control its behavior. So these can control things like the model's complexity. So you could have the number of if-else statements or the number of matrix multiplies you do. And if you have the same sort of model with the same data, but you use different hyperparameters in that training algorithm, your model will produce different predictions. It will have different floating point numbers inside it. And neither of these things, that the hyperparameters or the data, is really stored inside the model itself, which causes a bit of a problem when we want to try and deploy machine learning systems, because how do you track those models, figure out what's going on? How do you debug failures in that environment when you've lost the link between the model object and the things that created it, that are the things you can actually change in the system? So just a little bit about machine learning. We're going to talk a little bit more about actually trying to use those models. So, as I said, we're really just expecting things that take in a floating point array and emit a floating point array. So how do we actually do something useful with that? Well, in general, the task of running the model when you take in an input and produce an output is called inference, as the term of art. But most of our problems just don't look like, here's a float array, give me another float array back. It's like, read this database table, produce an estimate for next quarter's figures. You want to tag, like take in some image and tag all of the animals that it finds in it. Or you want to take in a piece of text and you want to tag all of the people, places, and locations that it finds in that text. Now, to do that, you've got to convert the data that you care about, the text or the images or the database table, into features suitable for the model. And then you have to extract whatever output you actually care about from the float array that it gives you back. Now, machine learning libraries usually sort of provide that core training and serving functionality, the sort of dealing with the floats, basically. But getting the data into and out into the floats and then parsing the outputs from that, it tends to be left to the developer who's integrating the machine learning model into their system. You have to wrap all of your models in supporting code that does these transformations. And that code needs to understand what transformations need to apply to what specific model it's running. And that will usually be different for every different model that you work with. So that's quite different from how normal programs behave. We're sort of Java developers in the main. And it would be really nice if the machine learning tools we had behaved a little bit more like the regular code that we use every day. So this is part of the reason that our group in Oracle Labs started building these tools, right? We wanted to be able to spread machine learning inside Oracle, inside the company, to help it incorporate this new technology. And as you might imagine, a lot of Oracle's technology is built on top of Java. And so we sort of looked around and there wasn't really something that kind of met all the needs that we had for the system. So we built one ourselves. We open sourced it in 2020. It's developed in the open on GitHub. That's the repo of record. You can see all the development that goes on there. It's under an Apache 2 license. You can contribute under the Oracle Contributor Agreement, which is a fairly straightforward thing. We have a nice website with some documentation and design done by people who are professional designers, not me, crucially. You can find the link to GitHub where all the source is. We've been using this in production for a variety of different things inside Oracle for more than 4 years at this point. And it's also been integrated into the OpenSearch fork of Elasticsearch to provide some machine learning functionality in there. The current version is V4. We actually open sourced it with V4 because we had 3 internal versions and we didn't want to confuse our numbering system. That runs on Java 8. We're working on V5 now, and we're moving to Java 17 because it looks like a lot of the fields going there, and we'd like to be able to use some of the new language features, to be honest. And our goal is really to provide equivalent functionality to the Python scikit-learn library, but on the JVM, because that's where we are. So we have implementations of lots of different machine learning algorithms and any other like third-party libraries that are available on the JVM, we have interfaces to a variety of those. We can also serve models that were trained in other packages or languages. So we can serve a particular kind of thing called ONNX models, which can be exported from lots of different Python packages like scikit-learn or TensorFlow or PyTorch. And you can serve those in Java in the JVM using Tribuo, which I'll talk about a little bit more later. So, as I said from the start, we built Tribuo because we couldn't really find anything that was really suitable for our needs, which was trying to deploy machine learning models inside large enterprise applications like the ones you might expect we build at Oracle. So, in addition to the sort of core machine learning functionality, the things that deals with the floats, it provides the data loading and the featureization that you need to be able to train a model and make predictions with that model to run the inference. It also provides a bunch of evaluation functions that let you measure the performance of those trained models. And sort of everything operates on objects. There aren't like primitive arrays and user-facing methods. We wrap everything up and try and be sort of fairly good object-oriented code. You can go and poke the floats if you want to. We're not going to stop people, but you don't have to be able to use the system. So for this reason, right, Tribuo models can't accept a float array and they don't emit a float array. That's not useful. We accept example objects that have more structure that we can reason over, and we produce prediction objects that, again, have structure that we can reason over. And the models internally convert the named features from the example, and I'll get into that a little bit later, into a float array. And then they take the outcoming float array and rewrap it into the named prediction object that you can easily inspect. If you sort of incorporate new data at prediction time, that can occasionally confuse other systems, confuse other models. We have sort of clear guidelines about what we do. We ignore them and they're treated in a specific way. And one other thing is if you're working with objects, but you have to get into the float array, you're going to have some kind of mapping function from those objects to the float array. We manage those for you. You don't have to worry about them. If you see them, that's, you don't ever actually have to see them to be able to do something with the system. Previously, we've sort of built this before, and we had to manage these mappings ourselves, and it got very tricky, and you could get them confused. And when you got them confused, your system just stopped working for inexplicable reasons. So this is a sort of rough overview of the architecture, which I'm only going to go through because it makes the code examples and a few more slides slightly more comprehensible. So we have some variety. We support a bunch of input formats. You can read things in CSV or JSON, or text, or from a database. Basically anything that comes in kind of a columnar format, you can write a processor, and we have a lot of support for writing that. We expose a few, but obviously there's more formats than we have developed interfaces for, but you can add them. And you take from that format and you go into a data source format, and that's the point where you do the sort of ETL step, where you take the information in and you construct things that are suitable for doing machine learning on it. You can then pass data sorts into data sets, and those can be saved out and they can be transformed, and they have much better tracking information, and they build a lot of metadata up. To take a data set and actually produce a model, you need a training object. That trainer object captures the algorithm that you're going to use, whatever the sort of actual system is for doing machine learning, all the hyperparameters, any of the details necessary to produce the particular output. And then you can combine a data set and a trainer, and you get a model out. You can save those out as well if you want. And then you feed in new data points to get predictions, and you can pass your predictions into an evaluation system, and it will produce performance metrics. This is a lot of types. It will make more sense when we step through the code example a little bit later on. You can also configure the data sources and the trainers. We have like a configuration system that accepts a variety of file formats, and will sort of build pipelines for you. So we sort of cover a fairly wide variety of machine learning prediction problems. So we can do things like anomaly detection, which is trying to figure out if one input is very different from the inputs it's already seen before. We can do classification of a few different kinds. We can cluster your data together. If you don't have a particular outcome in mind, you just want to try and do some analysis of that data, you can run a clustering algorithm. And we also support regression. So regression is predicting real values rather than a particular subset of classes. We have multiple algorithms for each type of prediction problem. As I said before, contributions, if you want to add a new algorithm, those are welcome. We have configurable ETL pipelines for dealing with columnar and text data. And those pipelines actually end up stored inside the model, which means you can always inspect them if you need to look at the model and figure out what it is, or what you have to do to the data to get it to come in. And the other thing that we added to the system that we think is really important, and which I'm going to go into in quite a bit more detail, is this notion of model provenance. So the provenance sort of describes the training algorithm, the hyperparameters, features of the data, where it came from, any transformations you did inside the JVM where we can see them. And that captures all of that in one object, which then lives inside that model, which means that these models are sort of self-describing. The model knows where it is, what it is, and where it came from. So it can tell you a lot more about its structure and how it was created. You don't have to store that information elsewhere. So we sort of working in this ML feature space, as I said, a lot of the times these models expect float arrays. We don't really want to work with float arrays because it's easy to get them wrong. And also, in a lot of the enterprise problems that we're working on, they tend to be large tabular problems. Like we pulled in data from some database table. We did some number of joins. Some of the joins might not be complete, right? So there might be some missing values. There's lots of sort of complexity when you're working with that data. But there's extra information there. You have all these columns. You have some structured source. You know more about where that data came from. So Tribuo's view of data and features in general is that everything is sparse, because then we naturally deal with missing values. If it's just not there, it's just not present, and that's okay. We don't have to deal with it. And all of our features are named because we're assuming that they usually come from some processing on some database column or some other structured input as JSON or a CSV file. So we know a lot more about those features, and keeping that name all the way through the pipeline makes it a lot easier to debug, because it came from that database table. I'll go and look and see where the data is and why that's behaving strangely. As I said earlier, we manage that name to index mapping, and we manage a mapping from the output names, like whatever label you're predicting, whether it's a cat or a dog or a 0 or a 9 or a 4 or whatever. We manage those in the same way. Because everything is implicitly sparse and things are named, features which weren't present when the model was trained are just ignored in the computation. And we do that because those unseen features don't have any model parameters associated with them. If it never saw them in the training data, it doesn't know what to do with them. So they can't possibly affect the output, so we just elide them away. In other systems, when you're feeding in a float array, if you make that float array the wrong size, it just crashes, because it can't find things it was expecting to find, or it found too many things and it's not happy. So we sort of make the system robust to that. This is particularly common when working with these large tabular problems. If you end up doing a different join 3 months later and the database table has changed, it won't crash your system. It will just note that something is a bit different. For that reason, we record the number of features that are actually used in every prediction, and sort of together, this sort of set of features helps us catch mismatches between when the model was trained and when you've deployed it in production, because any mismatch there can cause problems with your model's fit. It can cause problems with the model's performance. That's something you need to keep an eye on when you've deployed a machine learning system. Okay, so I said we're going to talk about provenance for a little bit, and we're going to talk about it in some detail now. So the provenance is a record of basically how any model or a data set or an evaluation came to be in Tribuo, how it was constructed. It's comprised of two parts. So there's the configuration, which is whatever the user told you to do. Like the user said to use a particular training algorithm, or to do a particular kind of evaluation, or to load in a particular data source. We capture all that information. We also have instance metadata. So this isn't things that the user told us to do, but it's metadata that was generated as part of the computation. And also, due to the way it is, that the instance metadata is users can add tags to things. So if you want to tag a particular model with a Jira ticket, or a particular timestamp, or it's for this particular customer, you can put that extra information in there, and then we preserve it for as long as the provenance is around. This sort of provenance generation is automatic. Every data set, every model, every evaluation construction makes one of them, and it's immutable on construction and stored in the object. And it's pervasive. Basically everything in the system that you will want to understand where it came from captures provenance information that tells you where it came from. So the trainers capture it, the ETL pipelines, any dataset transformations you do, if you want to ensemble a bunch of models together to make joint predictions, and even externally trained models, when they're loaded into Tribuo, we capture how they were loaded in, we capture all the information that the user provides at that time, so we can record them in the same way. And it's stored inside the model object, both in memory and on disk, because that means you can't lose it. You can't accidentally delete the Confluence page that recorded that information. You can't delete the text file where the data scientist wrote it. It's in the model. If you have the model, you've got all this information. Because frequently we would put it in a Confluence page and then lose the Confluence page. So we decided to avoid that problem. This provenance system is sort of built on top of a user-facing configuration system that I alluded to earlier. It can configure data sources and trainers and transformations. This system is actually open sourced. It was developed in Sun Labs in the mid-2000s for building speech recognition pipelines, and we've sort of been maintaining it internally for a bunch of our uses ever since then. It supports configuration in a bunch of formats, so it can do XML, it can do JSON, it can do Eden, which is like Clojure S expressions, because one of the guys in our group really likes Clojure and S expressions, and protobuf. You can also override all this configuration on the command line. We have an arguments parser that integrates to the configuration system, and it understands and deals with all that. So the provenance system just automatically, like the configuration is set as part of object construction, whether you use the configuration system or not, if you construct them programmatically. And so the provenance system just goes through the object, inspects all the configurable fields, extracts all that information recursively. As I said earlier, we actually also capture a lot of metadata about the ML system. And that's because these systems really generate a lot of that during the training process. They generate how many features they worked on. They know the number of samples they had. They have like distributions, like the different values the features could take and the number of times those values occurred, and same for the outputs. We also actually track system level features like the operating system, the CPU architecture, and the JVM version. We do that because it turns out Java is not as uniformly cross-platform with respect to floating point as you would like it to be. There are differences between Java 8 and later versions, and between Intel and ARM CPUs, x86 and ARM CPUs, in how some of the math functions behave. So we need to track this information so that we understand how the model was created. And if available, we have, like if you're loading in a file from disk, we're going to capture file level metadata like the hashes and the timestamps of those files, so we can validate that the training data for any given model is what we expect it to be. And so we're going to capture a huge amount of information, and I've talked about it for quite a while, and you might ask, why are we doing this? Well, there's a few different uses that we came up with, and we've collaborated to build a few more. So the first one is you can check that your input pipeline for processing inputs into the model is correct when you've deployed the system. Because the input pipeline is part of the provenance, you can validate it against the one that you've constructed, and you can even pull it out of the provenance if you lost it. And so you have that information. It's quite hard at that point to feed data through the wrong pipeline to a specific model. As sort of mentioned before, you can also use it to track these models in production, because the model is self-describing and you can poke extra metadata into it if you want to. The model knows what it is and where it came from. If you have the model object, you have all the information about it. You don't have to look at an external source, which may be lossy, or it may decay. We also then work with the Systopia lab at the University of British Columbia, who were very interested in provenance for systems more generally, and like for computer systems in totality. And so we worked with them on figuring out how to reproduce models that we'd already trained on new data, using the provenance information we have. So we could reinstantiate the trainer, we could reinstantiate the ETL pipeline, ensure that all of those things were identical, and then rebuild the system. Or you can also use this for regulatory reasons. If you need to validate that a specific model can be produced from a specific data set, either to validate that a particular user's data was included or wasn't included, you can then run that computation and validate that the provenance is the same and that the model is the same. You can also compute diffs of the provenance between different models. That's quite useful if you've got a bunch of different models in production. They're performing differently. The sort of provenance diff can tell you what things are different between these two systems, which helps you run down where those performance differences come from. And finally, the most recent thing we've worked on was automatic generation of a model card. A model card is a description format that's quite widely used within the machine learning community to describe models and their benefits and their considerations for using them and things like that. You'd have to write that all by hand, and it's quite irritating to do so, but the provenance information actually gives us a lot of the data that you'd expect for the model card, so we can auto-generate it and pre-fill it for you. You might wonder, isn't this provenance information a bit of a security problem if I have to give the model to someone else? And yes, it's got a lot of information, and it may have data that you don't want to leave your firewall. So for security reasons, you can redact provenance information at various levels and various granularities before deploying that model outside of the firewall. This is opt-in because, a lot of the time in the process of data science, you're going to create lots and lots and lots of models, even if you do actually want to ship one outside somewhere. And so we think that defaulting to automatically generating and creating the provenance information is much better than forgetting to turn it on for the 5 experiments you ran to create a particular model. Okay. So we're going to run through a quick demo of training models and provenance in Tribuo. So we go through the Zoomception that we had there. So this is actually a notebook that is in the Tribuo repo. And this is like the talk that I gave at Java 1 a couple of weeks ago. So it refers to Java 1 a couple of times in the text, but we're going to ignore that. So if you're not familiar with Jupyter Notebooks, they're a sort of interactive programming environment, which is very, very popular in Python. You can do it in Java. I'm just going to restart this kernel and hope that everything just comes up fine, which it did. So we're going to operate, and we're going to run through a quick classification system on a data set called MNIST, which is handwritten digits. I'll explain in a little moment. This setup stuff I've already done. The first thing we have to do is we need to load in some jar files. We have to point it at the class path, and then we're going to import a bunch of things, which I'm not going to talk about too much. So after we've got past the sort of standard things you have to do, the first thing we need to do to be able to train a machine learning system is to actually load some data into our machine learning system. So we're going to instantiate 2 data sources, this training one and this test one, and then we're going to fold them into data sets, and it's going to print out a few things. So as I said, this MNIST data set is a data set of handwritten digits. So they were drawn by people. I think they're taken from like the US Postal Service and zip codes. And we basically have like black and white pixel intensities, and we have 60,000 of them, which you can see from the loaded data. It's a 28 by 28 grid, which is 784 possible features, but 67 of them are just completely black all of the time. They're never actually got values in, so Tribuo just ignores them as part of the sparsity that we have. And there's 10 different classes for the 10 different digits. So we've loaded the data in. We loaded in a test set that we're going to use later on to evaluate the performance. And we created a couple of Tribuo sort of incidental classes, one evaluation factory and one factory just for dealing with the particular kind of prediction problem, which in this case is classification, which means we use a label factory. So we've loaded the data in. The next task is to define the model that we're actually going to train. We're going to use a very simple model, which is called a logistic regression. That's basically going to draw a straight line through the feature space. It's sort of the first and like the default option for training a machine learning system. It's fairly simple to explain. It's fairly quick to train. So we're going to instantiate the trainer. We're going to train it logistic regression using an algorithm called stochastic gradient descent. In Tribuo, that's represented with a linear SGD trainer. We have to tell it what thing we're trying to minimize, what function it's trying to, how it should measure how close its function is to the ground truth function, which is going to be a log loss because that's a fairly standard. That's what makes it a logistic regression. We're going to use a particular algorithm called AdaGrad. That there's lots of different kinds of gradient descent algorithms. They keep coming up with new ones every week. This is a fairly well-tested one from about 10 years ago that works pretty well and is a fairly good default for this kind of problem. we're going to tell it how many times it should look at each training example. So machine learning computations tend to be iterative. They tend to go through the data in waves. So we're going to go through the data 3 different times, look at each example 3 times, and use that to fit our function approximation. Then we're going to ignore this logging actually because you can't see it in the Jupyter notebook. It just prints the terminal behind. And we have to give it a random number generation seed because there's some randomization in this. This is why this algorithm is stochastic. So we've made this training object, which encapsulates all of these different things, which are the hyperparameters of the system, and this, which is the training algorithm. So we're going to set it training and capture the time. We basically take the trainer, we call train, and we feed it a dataset object. I'm also going to poke in some extra provenance information just so that we can look at it later, just to show how that is done. So it took about 6 seconds to do that. It takes more or less time depending on how much my laptop is loaded, but it's pretty quick. So now we've got our model object. It's LR model, and that is something that we can introspect and try and understand its behavior. So the first thing we're going to do is evaluate it. So we take our evaluator, we ask it to evaluate, we feed it a model, and we feed it some test data that's already been labeled. And we're going to measure how well the model's predictions compare to the test data that's already labeled. So that doesn't take very long either. And then this is part of the evaluation output that I mentioned earlier. So this is just the default toString. There are gets, there are getters for every one of these parameters, and you can sort of construct extra things as well to evaluate. But a lot of the time we print this toString output and paste it into a page to show to management. So we have good quality toString output. So this tells us the different classes. So it, as I said, it's handwritten digits. So we have the digits 0 through 9. This N tells us how many of each digit is in the test set. TP is the number of digits, the number of that digit it got correct, where it correctly predicted a 0 and it was a 0. False negatives, FN, that's the number of times it was in fact a 0, but it predicted a different digit. And false positives is the number of times it predicted 0 when it was a different digit. And then you can aggregate those values using things like recall, precision, and F1, which are various performance measurements, which are functions of these true positives and false negatives and true negatives, and false negatives. But we can also compute single values, just like the accuracy. How many of these did we get correct? We got 89.9% correct of the 10,000 test examples we had. You can average the recall, precision, and F1 in a few different ways, and there's different error metrics. So we sort of compute a bunch of data and display it to you that lets you sort of understand how the model is behaving for the prediction tasks that you've got. And we have different kinds of evaluation and different outputs depending on what the actual prediction task is, whether it's regression or clustering or anomaly detection or whatever. For classification as well, we can also produce this confusion matrix. So what this is when I predicted a 0, how many times was it in fact a 0? And so, like, did I predict any 1s as 0s? No, I didn't. I did get a little confused between 6s and 0s. And you can sort of imagine, like, why these are sort of more likely, right? The 0 and the 1, well, the 0 has a loop in it, and the 1s don't usually have a loop in it. It's not likely to make that kind of misprediction. But a 6 is a little bit close to a 0, and 7s and 1s tend to be a bit mispredicted. 4s and 9s, but you can sort of look at this data to see how your model is behaving, and this is and sort of use it to determine if it's going to be appropriate for you to deploy it in production, right? If you have a bunch of different classes, you want to ensure that it works pretty well across all the classes that you care about, and that it doesn't make any sort of egregious mistakes. As well as like having a toString output, you can also actually dump things out to a HTML table, and there's other ways to access all this information to print it out if you need to. The last thing we're going to check on is, I was talking about all this provenance information that we capture, so we're just going to inspect it quickly. We're going to convert it into a slightly lossy JSON format, but there are a bunch of different formats you can print it out in, and it's all actually machine accessible, right? It's just some objects that we can query. So the first thing we can see, based on the ordering of the map today, is that the extra information that we poked in at runtime. So this is where you'd see extra stuff that you wanted to record as part of that particular training run, whether it was a Jira ticket or some text field about where this model came from. We capture the version of Tribuo that was used to train it, and the Java version. This is a pre-release version of Java 19 because that's apparently the default JVM on my computer. And then we come on to the trainer. So this is where we've captured all the information from the trainer field that we fed in. So we see the random number generator seed. We have the Tribuo version again. We see some hyperparameters we didn't set, like the mini batch size that was defaulted. We see the ones we did set, like the number of epochs, the number of passes through the data. And we see like the optimizer. So we see it's an adograd object and it has these parameters. We capture the architecture of the machine. We capture the timestamp. It was trained a few seconds ago during this talk, and it's running on my Mac. We also capture all the information about the data set that I said. So we have the number of features, the number of examples, the number of outputs. We capture the data source, where it was loaded in from. So this is the path to where Tribuo lives on my computer. We have the timestamp for when the file was modified, and we have the hash, the SHA-256 hash of those files, which we can use to validate the next time we want to look at this model that we still have the same training data and it hasn't changed on us. We also get to see if there were any transformations applied. There weren't, but we would capture those there, and just some other metadata about the training procedure. Okay, so that was a very quick sort of run through of that. We're going to go back to the talk. I have a few more slides, and we're going to do another little demo, and then there will be plenty of time for questions. Okay, so we saw how to train a machine learning model in Tribuo very, very quickly. We have much more detailed tutorials on the web. You're welcome to look at those. But lots of machine learning training happens on platforms other than the JVM, much as we might like it to be on the JVM, but we still want to deploy them in Java so they integrate well with the larger application that we're building. So Tribuo supports a bunch of different models from trained by external systems. We can load in TensorFlow save model. We can load in TensorFlow save models. We can load in ONNX models, which I'll get to in a moment, and we can load in a package called XGBoost, the models generated by that. They all get wrapped up in Tribuo model objects, and they're used like any other model. They behave exactly the same as things that were natively trained. We also support wrapping the OCI, the Oracle Cloud Infrastructure Data Science model deployment. There's a REST endpoint that lets you deploy models on Oracle Cloud. We've wrapped those into Tribuo models just sort of to see how that behaves, and you can support deploying to that platform as well. And this allows users to deploy models that were trained in Python or other languages inside their Java programs using fairly familiar interfaces that behave like other programs they understand. So I've mentioned a bunch about ONNX, so I'm actually just going to talk and explain a little bit about what that actually is. It's an acronym short for the Open Neural Network Exchange format. It's a cross-platform model specification format that was originally developed by Amazon and Meta and Microsoft. It's now part of the Linux Foundation and is sort of managed as an open source thing. It was originally built for PyTorch to deploy deep learning models. A little bit later, support was added for exporting other machine learning models beyond neural networks, like things from scikit-learn, so you can export tree models, support vector machines, and things like that. And you can get into ONNX format from lots and lots of different machine learning frameworks. And then once you're in ONNX format, you can run those models on many different devices. They support edge devices, a wide variety of strange hardware. I think you can deploy them on IBM mainframes, right? So they're widely deployable. We actually built ONNX Runtime support. So ONNX Runtime is a library from Microsoft that lets you deploy ONNX models. We wrote the Java support for that library. We contributed it back up to Microsoft. And we maintain it in their tree. And this lets us deploy ONNX models in Java seamlessly. It's very easy to do. It can run on GPUs if you want to, and you have them available. And it sort of helps get more machine learning running in Java. Now, you can import models into Java using ONNX Runtime, but writing them from Java is a right pain. The ONNX format itself is just a protobuf, but valid protobufs are not necessarily valid ONNX models. There's a bunch of sort of restrictions on the format you have to deal with. We actually added support in the Tribuo 4.2 release from December last year for writing out ONNX models from Tribuo models. So you can take a Tribuo model, you can export it into ONNX format, and then you could deploy it in elsewhere. So you can deploy them in any platform that runs ONNX runtime. The ONNX writing support that we have is a standalone library. It can be used by any other libraries to write ONNX models on the JVM if they want to. Basically, anything in Tribuo which implements a particular tag interface can be saved in this ONNX format, and then you can deploy those models in Java or Python or C# or JavaScript or C via ONNX runtime or any of the other places where the ONNX file format is supported. So you get quite a bit of reach from being able to export to this. So we're just going to run through the other half of my Jupyter notebook. When we want to deal with these external models in Tribuo, Tribuo has quite a different view from them, right? As I said before, a lot of these systems expect to get a float array and emit your float array. If we want to make that into Tribuo, we need to tell Tribuo how to deal with those float arrays and how to interact with them. We do all this automatically for the models that are built by Tribuo. It knows all those things, but you have to give us a bit of help for external systems, and that's because we won't know the mapping from Tribuo's feature names to the index that the float array that should be living, right? So if you have a particular feature which is called price per unit, you need to tell Tribuo what index in the float array the price per unit feature should live. We're going to go through that sort of mapping procedure quite quickly. We're going to load in a bunch of sort of ONNX specific things. So we're going to work with a dense data set because MNIST is basically a single row of pixel values. It's not sparse in any way. And we're still working with labels. We're still doing classification. So we need to make these two classes which help manage the transformation into and out of Tribuo objects. We're going to define the path where we're going to load it from. It's an ONNX model that's in Tribuo's tutorials. And then we need to instantiate a couple of things just to make ONNX runtime happy. Because this is from one of our sort of tutorial models, we're talking about how we do that mapping. Normally, in a lot of cases, the mapping might be quite straightforward. If your columns are numbered from 0 to some number, then Tribuo is just going to use those as the feature names and emit them directly. So in MNIST, in the case of MNIST, it would be reasonable to have feature names 0 to 783 representing the 783 pixel values. But that will be a very boring mapping, and it wouldn't expose the test out the functionality, which is what we're trying to do. So we basically inverted this. So feature 0 in the model that we're loading in is the feature that Tribuo knows as 783 because it's the last feature. So we just have to do that transformation. So we create a map from names to the integer values that represent it. We also have to do the mapping from the label values to the integer values that those represent, but that one we didn't do anything funky, so it's just the label name passes an integer. And then we create this ONNX model. We pass in the mappings, and then we pass in the path where it should look. And also the ONNX model expects named tensor input, so we have to tell it what tensor it should map to. But now we've got a model, and it behaves like any other model. I should have run that. It behaves like any other Tribuo model. It's just a model object. We can evaluate it exactly the same way as we would. We have our evaluator object. We call evaluate. We pass the model in. We pass the test set in. And then we're going to print out the result of the evaluation. This takes a little bit longer, but not too long. And we see we have the same output as we got before, or at least very similar output. It's the same format. Due to the way, this is using the default hyperparameters from scikit-learn, and we use basically the default parameters from Tribuo. The default parameters on scikit-learn work slightly better on MNIST, so they get 92% accuracy, where we get 89.9. We could tune Tribuo's parameters to get this value, but I didn't bother doing it for this demo. And we could tune scikit-learn's parameters to get Tribuo's number. It's all sort of much of a muchness. So we managed to load in that model. We can evaluate it, and it behaves like other Tribuo models, but it was originally trained in Python. So that's pretty useful. We're also just going to briefly run through how we export the Tribuo model. So we just call save on it. You have to give a few extra fields of metadata. They need a namespace and a version, and then the path that we're going to write this out to. And then we can load that ONNX model back in as if it is trained elsewhere, and that lets you unify your serving platform. If you want to just use ONNX runtime to serve everywhere, you can do. I mean, you can always save out Tribuo models at ONNX format, but we could load them back in if need be, depending on how you want to do deployment. Again, because we're loading this model in as if we'd never seen it before, we have to produce the mapping. But here we get to cheat because Tribuo knows what the mapping is. So we just pull out the name of every feature and write the ID number for every feature in, because Tribuo already maintains this information. This is basically the only time where you actually need to look at inspect these values. So that's sort of one place where the abstraction is intentionally visible. And then we can load it in again. We give it a slightly different path. The input is named slightly differently just because of the default value that Tribuo uses, but we're still going to use the same classes that do transformation, and we pass in the slightly different output values. And again, this is just a Tribuo model, and we can evaluate it in exactly the same way. And we can see that we get the 89.9% accuracy that we got all the way back up here. And the model is performed identically, even though we've exported it into a completely different format, and we're now running it using some native runtime that's completely separate from how Tribuo behaves. Okay. So we've had a very sort of quick overview of Tribuo, which is a Java library for training and deploying machine learning models. It's got a really strong focus on ease of integration into larger applications and tracking those models once they've been integrated. Everything operates on objects. We don't really deal with primitive arrays because we think that's not really how Java programmers want to write. And the models manage the mapping from the objects to the primitive arrays kind of automatically. The extensive provenance information that we capture makes it really easy to examine a model and figure out what it is, where it came from, why it's behaving that way. And we can also use Tribuo to deploy models trained in external systems, including models trained in other languages, and you can then export those Tribuo models in ONNX format if you want to for deployment in other systems. This is actually just one of the things that Oracle Labs is doing to support machine learning on the JVM. We contribute to a number of different projects as well as Tribuo. So I co-lead the TensorFlow Java project, which is the official Java API for TensorFlow. As I said earlier, we develop and maintain the Java interface for ONNX runtime. You can find that on Microsoft's repo. And we contribute to various of our machine learning dependencies where it's appropriate, usually getting everything to run happily on new versions of Java or where we found some particular issue. Actually, in the near future, we're open sourcing a JVM-based probabilistic programming language called Sandwood. This is more targeted at academia because probabilistic programming is much more a field of research than it is of deployment at the moment. But probabilistic programming allows users to specify machine learning models and deal with uncertainty in those models' predictions in a much more principled way. And because you get to deal with the uncertainty in a more principled way, you get a better idea of how well your model is working and how it's behaving on certain tasks. That'll be up on GitHub soon under the Universal Permissive license at that URL at some point in the nearest future. We're not quite ready with all the documentation yet, but we're working on it. Okay. That was the end of probably quite a speedy talk. Do we have any questions? I think I'll pop back over to the air meet and stop sharing now.
I have a question, maybe a stupid question. So when you import or export objects to ONNX, there is no provenance at all, or is there some provenance still being created or being saved?
So when we export things to ONNX, Tribuo writes out its full provenance information in a way that Tribuo can read. So it gets stored in a metadata field of the object as a protobuf, a text form protobuf, and we can read that back in. So if we are on the ONNX external model, we can then inspect the protobuf. We can inspect the Tribuo provenance if it exists and extract all the information we had. I've actually been talking with Intel because they're very interested in adding provenance, a provenance schema to the ONNX file format itself. We're sort of talking with them on and off about that. I don't think there's necessarily anything ready to go yet. But if there becomes like a standardized ONNX schema for provenance, then we'll make Tribuo interop with that as best we can. At the moment, we're writing it out in a format that will be quite tricky to read from languages that are not Java, due to the way in which we're storing things. But that's mostly because we didn't want to specify something in a completely cross-platform way at the time. Right, we're happy to interop with it when there is a standard, but there isn't one there yet.
So if you read a model that was created in Python, will it say something in the provenance? This was a Python model, and that's as far as we know, or something along these lines?
Actually, the ONNX format by default won't have any of that information. It will just have the file, right? There's basically no metadata. You will get there is some metadata that gets written out by default, which is basically what converter was used to generate the ONNX model from wherever it came from. And that's about it. And you can access all those metadata fields by querying the ONNX object that you get in Tribuo, but because there is like a free text map from string to string that you can write metadata into in ONNX, but there's no schema for it. So we expose the map and you can query it, but we can't structure it because there's no structure.
Mm-hmm. Did Tribuo already get? You said that it was used in one place. Do you see it getting into use by companies at this point, or is it just the very beginning?
I think we're still sort of starting. It's we're using it internally for a bunch of things, right? The OpenSearch integration was quite interesting. They found, like, the first thing was that they found some bugs in how we interacted with the security manager that Elasticsearch uses, which we hadn't run it on Java 14 under a security manager before, because that's a kind of a strange deployment environment. So that's quite interesting. They've integrated that. There's a bunch of people who ask questions, but we don't have tracking information, so I don't know what they're actually doing, and I'm not interested in having tracking information in the system either. So it's an open source project. People can use it as they wish.
So right now it is used in Elasticsearch.
Well, it's used in OpenSearch, which is the fork of Elasticsearch that's still under the Apache 2 license. And as I said, we're using it internally for a bunch of things.
Do you want to say maybe just a word what is the difference, the principal difference between the Tribuo, what you do in Tribuo, and the Java TensorFlow or other framework?
Sure. So Tribuo wraps TensorFlow, so you can use it from within Tribuo and using our interfaces. But the sort of work on TensorFlow is a little more lower level, and it's a little bit more like we take in a bunch of floats and we emit a bunch of floats, right? That's what that API is kind of expecting. That's what we're trying to build. The aim there is to build it so that you can do the same things in Java that you can do in Python. There's a lot, and the TensorFlow team in Python is much, much larger than the team we have working on it in Java. So we're a little behind where they are, but you can deploy models that were trained in TensorFlow in other platforms, in like Python, in Java, and that works really well. The training side of things is not quite as good for a few different reasons. We're still sort of building out the interfaces to make it easy to do. There's basically a lot of code that we have to translate from Python into Java to get the sort of equivalent performance. The equivalent ease of use. You can do all the things. It's just harder than it really should be. So that's sort of building out like core ML functionality in TensorFlow Java, whereas Tribuo, we're aiming to provide like a slightly nicer interface. We're aiming to integrate a bit better with everything else and sort of to manage more of the process for you. So there's sort of different aspects of it. But you can use TensorFlow Java directly, and that's totally fine if you want to get closer to it. Tribuo, some of the stuff that we do does add a little bit extra GC pressure, a little bit of extra overhead. So if you're really in a massively high throughput thing and you just want TensorFlow, you probably should use that directly. Similarly for ONNX runtime, if you're in a massively high throughput environment, and I believe ONNX runtime is deployed in a variety of companies, like we're using it at Oracle, Microsoft are using it, I think Amazon are using it, given the complaints that they had, and maybe Netflix as well. So there's a few people who opened a bunch of like, performance issues that you would only hit if you were hitting it very hard. So, okay, well, that's interesting. And so there you might want to use that directly if you're really hammering it and you want to try and get the maximum possible throughput. And we're looking at improving the performance of both those systems as well. There's always more work to be done, right? So we're just trying to build out, trying to make it easy to use machine learning in Java, because it's a bit of a pain. So I want to try and make that less bad.
There is a spec that is the visrec spec that's being put into Java.
Mm-hmm.
And so do you have anything to do with that, or compatibility with that, or what are the plans?
So the visrec spec is one more focused quite strongly on image recognition, and that's an area that Tribuo just doesn't really care about. So our focus is on the things that we're likely to hit in enterprise data. So that's a bunch of text, a bunch of database columns. That's where we kind of focused all of our efforts, because those are the problems we have. So we haven't looked too much into images. I mean, the example I used was essentially images for digit recognition, but that's because it's a nice visual example and it's easy to see what's going on. We don't tend to do that much of that. There's a bunch of performance work that we need to do in Tribuo to make it work better with large, dense feature spaces of the kind you get with images. And we're looking to do some of that performance work as part of the V5 roadmap, because we need to change a couple of the interfaces to make it properly extensible and fast in the way it needs to be. Because at the moment we make slightly too many objects for a large dense feature space than you really want there to be. We need a better tensor representation. The other aspect of that is that the visrec spec itself sort of believes that everything it's talking to is a neural network, as because the neural network builder is part of the API, and we don't have, we can provide that TensorFlow builder as a neural network builder, but we have a wide variety of other algorithms which we wouldn't be able to easily force into that API. So I'm not sure how best to do that kind of integration. You could bind TensorFlow Java to it, and you could bind ONNX runtime to it at prediction time pretty easily. I haven't done that. I'm not sure if anyone in the community has done it, but you could do that. I believe the team at Amazon behind the DJL did do a binding between DJL and the visrec spec, which will allow you to run MXNet, which is their primary framework, and TensorFlow and ONNX runtime up through their visrec interface layer up to the visrec JSR spec. But I haven't looked into that too much. As I said, our focus has not really been on image problems, so it's good that people are doing it, right? And we want to try and make it easy to do all of these things, but it's not where our focus has been.
Okay, I think we don't have any other questions or anything here. Okay, so I really appreciate you making this talk, taking the time and making this effort and showing here. This was a very not just interesting, but I think an important talk, and you did a good job, very good job presenting it in a fluent way. And I hope people will be using it more and more, and we will see Java machine learning applications coming up, and enterprise applications combining those kind of applications within them. So thank you again. We have been recording it, so we will have this recording on YouTube within a few days.
Excellent. Thank you very much for having me. I hope everyone found it useful.
Thanks, Adam.
Thank you for everybody that is here virtually or in person, and see you next time. Bye bye.